Today, today I want to introduce you to the lesson regarding the CUDA parallel programming, and I will make the following. I write the following code, and I want to sum the vectors in parallel form. Let's imagine that we have some array of numbers, array first array an, and the second array bn, and my main goal is to sum them and to write the result of the array of cn as you see here, plus bn, and will be defined as n which will be equal to the 20, and my main goal to use CUDA algorithm. And let's imagine that we have some computer, some CPU. First, this CPU will be called host. Then I want to realize this operation, but in parallel form using GPU. And there is a question how to make these two devices to know about each other. For the first moment, I have to create these arrays EAN, BN, and I'll write here some initial values within this CPU. It will be the first step. Second step will be copying of these vectors to the GPU device. Copy to GPU. Then I want to make a summation that was mentioned here, but this GPU will let us to divide these operations on some blocks, and I'll make this summation parallel. I mean, I will take this 0 array of C0 and I'll make the following operation. And I want to notice that these vectors are the copies of these vectors within this CPU. And let's mark them C1, GC, GA plus GB0 and GC1 will be equal to the GA1 plus GB1. Maybe you don't understand it's everything that I do now, but I will further write a code and I'll explain all steps that were done. And for example, I have two steps, and I will make them in parallel. I mean, I will divide this GPU on sections using some technology it will mention below, and realize this operation in the first one section, this operation in the second one section, and and so on. And I will make this summation for all elements of these arrays for E from 0 to n in parallel form. And the last step will be the copying of this array C, GC, which is the mirror of our C array, to the C but on the CPU. I mean, right here AN, BN, and take the CN and JC, return it to the CPU, and write the value of the JC to the CN vector, and print the output. And maybe this step will be operations. To the output, printing these values. Before I start to write the program, I'll mention that every type of the CUDA code will contain the following steps: initial conditions, copy to the GPU operations, then copying back some result and output. It is a common form of every program on the CUDA. But next, let's start to write some program. Let's select some file and let's call them, for example, program CUDA. And let's type some units in this program. Include vector. The second include will be used for the output. Then I using namespace std section int main. The CUDA code is enough efficient methods of parallel programming, and it's enough simple. There are some difficulties at the beginning, but then it will give you some huge advantages for your calculations. And let's write that we have some arrays of numbers. This example is of course simple too, but there is one important feature of this example. This feature is connected that it can help us to understand the main principles of GPU programming, BN and CN. I use of course Linux operational system, but if you write the same code on the Windows system, you will be of course correct. And now I'll write here some pointers that will give us the possibility to realize copies on the GPU of the written above arrays. And let's write some array that will help us to give some initial values to this array. Everything is that I write now doesn't contain any GPU code. E less than n, e plus plus, then I'll write a initial value, for example, e and second value of b will be equal to e plus e without any random numbers, and then the further row. And let's now allocate some memory using cudaMemcpy operation. cudaMemcpy void the sign of multiplication, then the following structure. It means that for this pointer that I have written here, I allocate some arrays of, in our case, integer values. And this array of integer values will be used to have the same size as these arrays. I mean, for A we have for GA we have the following array, because we will copy the array from CPU to the GPU, and it's only the memory locations. CUDA success, and let's copy the string. I don't want to retype it now. And as you see, I have connected to the server and make all operations within the server. CG, BG. Okay, GC, GPU B. And now, I want to return the. I want to make some output of my program. E less than n, E plus plus, C out. And so on. And let's make some output. Within the string. For the first month, when I have started to apply CUDA for my scientific investigations, I was against this method because I have always been working partially with the code without any idea of parallelization. But when I have understood that my calculations are too slow, I have decided to study this new technology, and for some kinds of codes within C++ programming, I have gained the growth in speed around 100 within of times. It doesn't mean that every program that you write will have such huge growth in speed, but for some simple programs, for example, which are comparable to the program that I write now, the growth of speed can be very sufficient. Of course, it used to be defined not only by the ability of programmer to write some parallel program, but of course by the properties of some target video card. And now I'll have I copy some arrays from CPU to the GPU. You see here that there's the array for which I have allocated memory in the previous step, and this array that I'll copy now. I copy array A to the GA pointer that is allocated within the GPU, and memory was given previously. And I make here this step of copying. I have make some summation now. N1 GA BG GB CGC, and of course I'll have to copy back the C to the device. And you see here three signs of more, and this is one of the difference in comparison to the non-parallel code. This function should be given above, and I'll write it now. But previously I want to make the operation that was mentioned below, to copy C back to the host. And now, of course, I'll define the amount of memory that I want to copy. Everything is very simple. cudaMemcpy copies some informations. C is The first letter identifies the place where I do copy. The second identifies what do I do copy. And this is the size of the structure that is being copied. And you must understand that the structures must have the equal size. And now I define the direction. The direction will be given from device to host. And our device is, of course, our GPU. And let's write here some global function that is given as add. I'll give some pointers here. Int a, integer b, integer c, and let's write it here. Integer id, and now attention, the parameter that lets us to make its all in parallel form. And let's discuss this function much more attentively. C, id, and the realization of this summation. A, id plus b, id. Let's discuss this. What does it mean? What this function does mean? I have mentioned below that make is parallel, and this parameter block idx is the number of this block. That's why if I'll watch this code again, I say that this function h will have its own copy on every from these unit blocks. Add, and for every block this value will be equal for the first one 1, 0, 1, 2, 3, and so on. Add, and if you will consider this function, you will understand that for the first block you will have the following function add, id equals 0, for example, and if statement 0 less than n, c0 plus equals a0 plus b0. For the second block, id equals 1, block idx is 1, then we'll write the if statement 1 is less than n, and I'll make the following operation: a1 plus b1. It's the second, and as you'll see much more attentively here, you'll see that this parameter will be written in this place, then will be compared to this, and this statement is used only in the case if the amount of blocks more than the amount of elements of our array. This will let us not to make the summations for the elements of the array that exceed the an, for example, and bn parameters. And all these operations are made in parallel. For example, it can be defined as we have, for example, some collection of computers, in our case for 20 computers, let's make, and every computer calculates its own, let's make its own operation independently. And let's compile this code and let's see what this code can give us. Clear NVSCC or CUDA Progress Q. We have again some error that identifies that we haven't previously identified the E pointer. Let's make it now. And let's write some script. Line spin and run CUDA. We have previously compiled, but I work within the clusters, that's why I have to make some compilation for the Windows system. It will be much more easier, but I don't have at this time of my life available Windows system with CUDA programming. Let's realize this within our cluster. CUDA, and with the following commands I'll state to the order and starts with calculations. Spin SGA. Calculations were realized, and let's see our result. Let's see spin SGA or 741. It's the usual Linux program, and the output is written to the text file. And you see here that I have realized some calculations. Let's make our output much more convenient for the view. One as usual. And some people ask me what kind of operations do I prefer, Windows or Linux? Of course, for scientific calculation, Linux is much more useful, because it gives us some possibilities to make much more efficient than in comparison to the Windows system. But Windows system has, of course, some its own advantages, and the main advantage is the simplicity for the applications for the beginners. Let's compile this code again. CUDA-proc. We have compiled it using this statement, and it is CUDA. It tells us to use CUDA name, and then write, then state spin SGA, and let's watch at our output. I'll mention again that if you have Windows operational systems, output will be printed in some window. Let's spin. We'll see here I have realized some output, and I have gained some result of their parallel walk. Okay, fine. Thanks for your attention, and with best regards to you. I'll try to make some lessons regarding CUDA again. If you have some comments, come to me and state. With best regards again, everything the best, goodbye.